In this video, I want to talk about the two problems that we have for today. Give you a little bit of background on those problems because they're going to be really important as we go forward with chapter 11 in terms of some of the issues that they raise. So the first problem we're going to look at is problem 62 in the textbook. Let's see if we can zoom in on that. 62 in the textbook. It is this. It is this cylinder, or it could be a sphere, and it is pressed up against a wall, and it has a string wrapped around it, and that string is going to get pulled upwards. And the question is, how hard can you pull up that string before the object begins to rotate? Okay, so that's the background in that problem. So let's just think physically about what's going on there. All right, so I have a cylinder here that I've wrapped with a string, right? And if let me just orient it like it is in the textbook. There we go. If I were to pull the string upwards like this, oops, right, our can is going to rotate like this. Now, in the problem, the can is up against the wall here and here. So what's going to prevent this thing from beginning to rotate then would be what? Well, if you said static friction, you're right. And so here's the thing with static friction. In the past, when we've talked about static friction, we've talked about a surface in contact. So what we're going to have to start thinking about now is not just the object being in contact with something causing static friction, but that static friction really only acts very specifically at the point of contact. So if this is the wall, the point of contact here is this point on the edge. So if this string is trying to get the can or the cylinder to rotate clockwise, that means this point of contact is trying to move downwards past the wall, which would mean that static friction would act upwards here, right? And this point of contact here, which is in contact with the floor in the problem, is trying to go, once again, if the object is trying to rotate clockwise, the point of contact is trying to move to the left with respect to the ground, and therefore would experience a static friction to the right. So that concept of thinking about the point of contact as having a static friction force, and that point trying to slip past or move with respect to the ground that it's in contact with, that's going to be the reorientation of our thinking. So it's not that the object is going to move past that point. It's that move past the point on the ground. It's that what is this point of contact doing relative to what it's in contact with on the ground. And so that's going to be the logic of problem 62. Okay. Hopefully you see that there's going to be quite a bit of limit work in that problem since we are dealing with static friction and wondering if something will slip. The second problem that I wanted to just have a brief conversation with, and these would be conversations we'd have in class if we were in class, so prior to doing these problems. The second problem that I want to talk about here is the gate problem, or as it says, old MacDonald had a farm, and on that farm he had a gate, right? So in this chapter we have monkeys, we have a bear on a beam right there, and now we have a cow by a gate, right? A very animal themed thing. But what I want to do here is talk about that gate, right? So hopefully what you're seeing is that the theme for today is two-dimensional objects, because in the past we've done like booms and beams, right, which are really just one-dimensional objects. But here we're dealing with the sphere or a cylinder, that two-dimensional object, and now we're dealing with this gate. So let's just draw the gate. Now, don't think of it as a gate. Think of it as a door hanging from two hinges, right? I'm not going to draw the whole thing, that gate, because I want you to think about the doors in your house. So you'll have a hinge here and a hinge here. Hinges are never done at the very, very top or the very, very bottom. They're always a little bit inwards, and they're not in the middle. Sometimes you'll have 3 hinges, but this particular problem only has 2, so I'm just going to draw 2. So I want you to think about what's happening here with this door, right? So a door that's hanging in a frame, let's say it's hanging freely. It's not like locked into the other side of the door frame here. It's just a door hanging freely. So if that's the center of mass, that's the force of gravity. So think about what that force of gravity wants this object to do. It wants it to fall straight down, but it can't because this door is artificially constrained by these 2 hinges. So the easiest thing to do is think about, well, what would happen if this bottom hinge was gone? Well, what this would mean is that this force of gravity would produce a torque that would try and make the door kind of swing in. It would sort of move inward and rest up against the door jamb here rather than hang freely, right? So that means that this point would want to pull away from the hinge, so the hinge must be pulling inwards here and holding the thing upwards, right? Now imagine if this hinge was the only one and that one wasn't there. Still, the door would want to swing clockwise like this. So what would that do? Well, that would put pressure on this hinge because the object would try and push into the door frame again. So this hinge would want to pull outwards or push outwards and once again hold the object up. Now when you have both, sort of an interesting thing happens that these two hinges end up splitting, holding up the weight of the object. But as this one maybe is trying to pull this object inwards, the door still kind of wants to rotate clockwise if it could because of the gravity force. So this might push outwards, right? These two hinge forces in a horizontal direction might do two different things. Now, in the problem that we're given, it's not just a door, there's also a rope here. And that rope is going to pull like this, which could pull this away because it's trying to rotate the system counterclockwise, pull away from that hinge, and therefore push in across the door to push inwards here. It all depends on what this tension is. And that's really what this problem is about, is playing with this tension to see how it changes the hinge forces, right? Now remember, as long as we're choosing one of those hinges to be the pivot, we can solve this problem. Another thing you're going to find out in this problem is that we are not, with the analysis that we're going to do, be able to tell what the difference between the two vertical components of this hinge force are. All we're going to be able to figure out is what are these two hinge forces vertically combined. And I want you to think about why it is so that we really can't make that determination. So that's something I want you to think about the old McDonald problem. The other thing that we want to talk about here is that, or just mention briefly here, because it's going to come up tomorrow, is that these hinges force the object, in this case the door or the gate or whatever it is, to rotate artificially about one of those 2 points, because that's naturally what it would do since there's an artificial constraint. And I want you to start thinking about what would happen if there was no artificial constraint. What would an object like that experience a torque rotate about if indeed there was no artificial constraint? So that's your question for today to think about. You're going to be doing problems 43 as well as 62 for tonight, and give those a whirl.